Hi, welcome to this tutorial. So supervised machine learning techniques are powerful tools for classifying satellite imagery into various land cover categories. However, one of the major challenges is the need for labeled training data. Collecting this training data on the ground or digitizing from very high resolution images is quite time consuming and costly. At the same time, we have access to an abundance of satellite imagery from missions such as Landsat, Sentinel, and ALOS PALSAR. These images cover the entire planet at regular intervals, creating a massive resource for analysis. Yet, we cannot fully take advantage of these datasets because we lack enough high-quality training data in order to build accurate machine learning models everywhere. So this is why scaling geospatial machine learning is important. Instead of building separate models for each location, we aim to develop machine learning models that work across different regions with similar geographic characteristics. So this idea is known as spatial transferability. In other words, we are interested in how well a trained machine learning model in one location can perform in another location. So in this lab, we are going to explore spatial transferability by using a model trained for a city in Zimbabwe. So this is the second capital city of Zimbabwe, called Bulawayo. So we want to use the random forest trained in that city in order to classify images for another city called Gweru. Okay. So here we are going to use the same images that we use for Bulawayo. We are going to use the same images for the new city. So that is we are going to use Sentinel-2 optical bands and ALOS PALSAR HV polarization image. Right, so by doing this, we would like to check if this model can generalize well to this new study area without actually creating training areas and retraining the model from scratch. Right, so our objective here is to understand this concept of spatial transferability in geospatial machine learning workflows, and we also want to apply the pre-trained random forest model in order to classify satellite imagery from a different study area. Right. So first we are going to import to install and import the libraries that we are going to use in this tutorial. So libraries such as rasterio and EarthPy that are used for processing satellite imagery, they are not available in Colab. So we need to install them first. And then after that we import this library as well as the other libraries that are available in Colab. So following that, we are going to set up our workspace. So we are going to mount a Google Drive. This is where our datasets are stored. Then we are going to define the path and the predictor variables and target variables. Right, so for the path, we are going to define the path where we contain the new satellite images for this new study area. So we have for Gweru Sentinel-2 for 2024, and then we also have ALOS PALSAR for 2024. So these images also come from the same date range as the images that we used in Lab 5 for the city of Bulawayo. Right, next we set up the path where the random forest model that we created in Lab 5B is located. Okay, so this is the best model. And then we are going to set up the path to the where we are going to store the land cover map for Gweru. So that is the new land cover map that we are going to create. So this is the output path. So for the predictor variables, we have our bands here. So these are Sentinel-2 bands and the ALOS PALSAR HV polarization image. For the target class, we have the land cover classes such as Bay Area, Built Up, Cropland, Grassland, Woodland, Water, and we also have the corresponding palette with the colors that represents these land cover classes. Like next, we are going to load the previously trained random forest model that we saved in lab 5B. Okay, so the model was stored as a Python object using the joblib library. So this is commonly used for saving machine learning models efficiently. So the joblib load model path function is going to read the model file from a specified path, and then it loads it into memory as a dictionary called a model package. Okay, so this dictionary contains two key elements, that is the model and the features. So the model stores the trained random forest model that we created in lab 5B. Okay, and then the features contains the predictor variables, that is the spectral bands from Sentinel-2 and the HV polarization from ALOS PALSAR. Right, so this is quite important because we are just going to use the same model without need to retrain it again. Right, so next we are going to load and display the Sentinel-2 and ALOS PALSAR HV band. So this is just using rasterio to do that. And then this is these are the images for the new study area. Right, so we have Sentinel-2 here stored in the shortwave, near infrared and red. Okay, so this is the central part of the city. Okay, here we have some developing residential area. So this is the ALOS PALSAR HV image backscatter, showing you again the central part of the city, and then we have the other parts of the residential areas here, very showing a very clear pattern. Right, following that, we are going to first to apply the model so that we can classify the satellite images and ALOS PALSAR for the new study area. Right, so what are we going to do? So we need to prepare the input features, okay, and apply the trained random forest model so that we can predict the land cover classes for the new study area. So first here, Sentinel-2 bands and the PALSAR HV image, they are stacked together. Okay, and then we are going to use here the NP concatenate function to do that. So the Sentinel-2, remember, contains 9 spectral bands, and then we have only one polarization image band from the PALSAR. So in total we have 10 bands that we are going to use, or 10 features that we are going to use here. Right, so this is what this is why we have this MP new access function, so that it adds these it takes these two different images from different satellite sensors. Right. So our band here, we have it in 3 dimensions. So we have the 10 bands, and then we have the height and the width. Okay, so we have height, width, and then the 10 bands. So this is how it is defined. Okay, so next, this array is transposed to the shape. Okay, to the shape, height, width, and then we have the dimension of the bands, the 10 bands, so that it matches the format that is used by scikit-learn. So scikit-learn models use a different format where each pixel is represented by a vector of 10 features. Right, so next, the stacked image is reshaped into 2-dimensional array. So this is where we need the flattening. So using the flat pixel. So of shape, that is the number of pixels, and we have the 10 bands. So that each row corresponds to a single pixels feature vector. This reshaped array is passed now to the predict method of the previously trained random forest classifier. Okay, so we are going to pass it here to the previously trained random classifier, so that to predict to create a new land cover map. So to create a new predicted land cover map. Okay, so finally, the predictions are then reshaped back to the original spatial dimensions. So remember, we have height and width. So these are the original spatial dimensions, so that we can produce a land cover map. Okay, so that we can produce it for visualization, and then we can also export it so that it can be used in different GIS softwares. Right, following that, we are just finally going to display the newly created land cover map, and then we save it and export it to Google Drive using rasterio. So this is a very simple method, and then this is the outcome. So this is our predictive land cover map for the new study area for this seat of Gweru. So we can see that actually the built up areas, they come out very well, and same was for the woodland and grassland and cropland areas. There seems to be a problem here with water, because there are some parts of the city here, these are not water areas, but they are classified as water. So this is problematic. This is because the original model from Bulawayo also had the same similar problem. So we need to revisit that model and then correct these areas, and then the classification will be will improve. However, as you can see, this is quite a cost-effective way to perform classification in a new study area without the need to create training data sets, which is actually time consuming. Right, so please use this code. I'm going to leave it in the description. You try it in your study area, and then try to fine-tune it. So thank you very much for watching this tutorial. See you in the next one.